Question number 1. A rectangular wire loop of length 5 cm and width 6 cm has no magnetic field through it. The magnetic field is switched on and threads through the loop at right angles. After 0.04 seconds, the magnetic field strength through the loop becomes a steady 0.4 teslas. Calculate the change in flux. Okay, the symbol for flux is phi. If we go to the formula sheet, see that phi is magnetic field times area. Magnetic field is 0.4 Tesla. Initially there was no magnetic field, so it would change from 0 to this maximum value. The area is 0.05 times 0.06, 0.4 times 0.05 times 0.06. Where's that to be 1.2 times 10 to the minus 3 Webers. Okay, B, calculate the voltage induced in the loop. If we head over to our formula sheet, we can see Faraday's law. Epsilon being the electromotive force is equal to the change in magnetic flux over the change in time. Let's make things easy for ourselves. Voltage equals negative. Negative comes from Lenz's law. Induced voltage equals negative d phi dt. The change in magnetic flux, well, this was initially 0 and now it's gone to 0.012, and it's done that in 0.04 seconds. We can chuck that into the calculator, and we get an induced voltage of 0.03 volts. Okay, coming down to question C. If the wire of the loop has a total resistance of 0.03 ohms, calculate the current that will flow. That's simply Ohm's law. I equals V divided by R, the voltage divided by the resistance. The induced voltage is 0.03 volts. The resistance is also 0.03. This gives us a current of 1 ampere. D, describe any further effect this induced current may have on a wire. Okay, you've got a current carrying wire. What goes around a current carrying wire? We know from last year that any current carrying wire will have a magnetic field, and you can use the right hand slap rule to work out which direction that is. Okay, so if we come up here and read the question, in question 1, there's an external magnetic field, there's a magnetic field around this wire. When the two magnetic fields interact, there's going to be a force. We can work out the magnitude of that force from F equals Bill, which says that the force that the wire feels is equal to the size of the magnetic field, the current, and the length of wire. In a more formal sense, the induced current creates an induced magnetic field, our red line, our magnetic field, our B field, which will oppose the change in magnetic field, producing it, the external field which created this voltage and this current. These magnetic fields will interact and produce a force on the coil. This force may cause the coil to move if that is possible. If this wire is fixed, obviously it won't move, but it will still experience a force. If the wire or coil isn't fixed, then it will be able to move.